We were on our journey to beyond the standard model physics. We argued that neutrino masses, dark matter, the baryon asymmetry of the universe provide convincing evidence that the standard model is not a complete theory of nature, and the fine-tuning problem of the Higgs mass and what's called the strong CP problem is theta term in the QCD Lagrangian, the non-perturbative one, require fine-tuning by respectively some 30 orders of magnitude and 10 orders of magnitude, which seems unlikely, and that the possibilities of grand unification and the Smolensen hierarchy in the parameters of the Yukawa sector and the mixing further tell us that there might be physics beyond the standard model. And it's an important question to understand at which scale do we stop the standard model to stop being a valid theory, and where there are new degrees of freedom that are not yet known to us and which we would like to know, or there are new forces whose range is so short that we could not see it so far. So that's the inverse of the energy scale, is the distance scale. It's also important for us to know whether we can build an experiment to directly probe these effects, or whether there are other ways of probing it, or whether we will never know the answer, which could also be the case. So the standard model cannot be a valid theory above the Planck scale of 10 to the 19 GeV. So the current, the electroweak scale is roughly 10 to the 2 GeV. So that's 17 orders of magnitude higher, because there quantum gravity starts playing an important role. We have a hint from the possibility of coupling unification. If they unify, then it happens at a scale of around 10 to the 16 GeV, still 14 orders of magnitude above where we are now. So for example here, there is no way that we will produce in our accelerators degrees of freedom that are 10 to the 16 GeV, but grand unified theories, all of them break baryon number, and so we might get a hint from proton decay that indeed further hints that indeed grand unification occurs. The seesaw scale, that's the scale related to the neutrino masses, is still, first of all, intriguingly close to the gut scale, and that's an important fact. And it hints at a scale of 10 to the 15 GeV. The neutrino masses of our order, the vacuum expectation value, we expect them to be lighter than the vacuum expectation value squared of the Higgs over this scale. Since we now know neutrino masses, we know something about this scale. I will explain this, so we will still have time somewhere between today and probably tomorrow morning when I discuss how do we deal with the fact that neutrino masses violate the standard model prediction. So all these are very high scales. We will not directly probe them. Maybe we'll get further hints from low energy to what is happening there. Like for this scale, our hint came from neutrino masses. But there were at least two strong hints to much lower energy scale, one that is in principle accessible to our experiments, directly accessible. First is Higgs fine-tuning scale. So around between a TeV and 10 TeV, the Higgs mass, if there is no cutoff to the standard model, the Higgs mass starts to being fine-tuned. So the scale is roughly 4 pi, the mass of the Higgs over the top Yukawa. It's explained in previous transparencies in this chapter, but I did not go over them. So if you are interested by that's the scale, then fine. mh is 125 GeV, 4 pi is in physics 12. In mathematics it's a little bit, has more digits, but sometimes it's even just 10, and sometimes it's even just order 1, whatever you like it to be in physics. And so 12 times the mass of the Higgs is around the TeV scale. The y of the top is 1. And another hint for the TeV scale came from the dark matter. So perhaps the best, dark matter could be many, many things, spanning some 40 orders of magnitude in possible mass between ultralight dark matter and primordial black holes. But the best motivated scenario is something called WIMP, weakly interacting massive particles. And this is based on the following consideration, which I may come back to if I have time for particle cosmology. And so if not, I'd rather state it now. So if the dark matter particles are interacting with the standard model particles, which is not necessity, we don't know if that's the case, but that's our chance to discover them. And they've been at some point in the history of the universe in a thermal equilibrium due to their interaction with the standard model particles. Then they follow the equilibrium density, which is something that we know how to calculate, until they become too rare, or the cross-section for interaction with standard model particles become too small. It's the cross-section times their number density, and their relic abundance freezes out. Now we know what the relic abundance is, and so from that we can calculate backwards what is the required cross-section of the interaction of dark matter particles with the standard model particles, so that the relic abundance will be the correct one. Okay, so that's the case if the cross-section is something like alpha weak over a TeV squared. And this scale that comes in, okay, just scale, calculate particles that have been in thermal equilibrium with the standard model, what should be their cross-section in order that you will have the right relic abundance of dark matter, and you get the TeV scale as a result. And it has nothing to do with electroweak physics. It comes from a completely different place. Actually, this is the average of the present temperature of the universe, the temperature of the cosmic microwave background, that's 10 to the minus 4 electron volt, and the Planck scale. It's a kind of a miracle that the geometric mean of these two scales that have nothing to do with the electroweak scale give us something close to the electroweak scale. And so if particles have cross-section of interaction with the standard model particles of the order of the W in the Z mediated cross-section, then they are good dark matter candidates. So that these are the WIMPs, the weakly interacting massive particles. Again, it could be a completely different scenario in nature, but that's very well motivated. In particular, because of the Higgs fine-tuning, we had excellent ideas of what kind of physics to expect at the TeV scale. Supersymmetry, composite Higgs were the two leading, and all of these theories that solve this had dark matter candidates in them, things that interact with the standard model particles at about this cross-section. So this was highly motivating, and that led to high expectation from both LHC that explored this scale to discover supersymmetry or composite Higgs or something else, and from experiments searching for weakly interacting massive particles, like the xenon experiment in Italy. And disappointingly, nothing was discovered there. So it could well be that the Higgs fine-tuning scale is just something in our minds, and nature doesn't care, fine-tunes or whatever. It could be that the scale is somewhat higher, a factor of 10, and the fine-tuning is therefore, I don't know, for order 10 to the minus 2 or 10 to the minus 3, which could be accidentally the case. And it could be that the dark matter is not weakly interacting massive particles. So if the fine-tuning is only a theoretical problem and not something that nature cares about, and if the dark matter is not weakly interacting massive particles, in a sense we lost a little our hint of where the next scale is. But it's still, we are exploring this because we can, and because perhaps the solution will still one day reveal itself to us with higher statistic or with a little bit higher energy. We'll see. So, said that it could be, the need for new physics could lead to two things. The degrees of freedom that are very light, but interact very, very, very super weakly with the standard model particles. These are now called, I think, feebly interacting massive particles, FIMP, opposed to weakly. In which case, the standard model, as I said, is not even a good low energy effective theory, because there are additional degrees of freedom at or below the electroweak scale that it doesn't include. The other possibility is that it is a good low energy effective theory, in the sense that all new degrees of freedom are considerably heavier than the electroweak scale. And in that case, there is a treatment of the effect of such new physics that is agnostic. It doesn't care about the details of what is happening at high scales. It encodes all possible effects of such high-scale physics. So if you assume the standard model is not a field theory of nature and the new degrees of freedom are heavy, then the standard model is an effective field theory, good up to the scale of a few hundred GeV or TeV, or maybe much higher. And in this case, you must add the normalizable terms to understand what can happen due to such heavy degrees of freedom. So if things are dimension 5 in the fields, their coefficient should be of dimension 1 over a scale. If they are dimension 6, then 1 over lambda squared, etc. So the Lagrangian of the standard model effective field theory start with the renormalizable one that we wrote down fully, completely, and analyzed. And then this higher order operator, first of all, they are product of the standard model fields. Okay, that's the definition of effective field theory. You do not add explicit degrees of freedom, otherwise it's not the standard model effective field theory. When we denote by this, we mean dimension n in the field, so the standard model is up to dimension 4, dimension 5, 6, etc. And this is a product of standard model fields that must be singlets of the standard model gauge group. And the effects of these higher order terms for n larger than 4 is suppressed by the energy at which we are doing the experiment, or by V over this scale lambda, which by definition is much larger than the electroweak scale, to the n minus 4. So suppressed more and more strongly as we go higher and higher in the dimension of the operator. So effects of dimension 5 term will be suppressed either by energy over lambda or by the vacuum expectation V over lambda. Dimension 6, V squared over lambda squared, or E squared over lambda squared, etc., smaller and smaller. So first of all, we expect the effects to be small, but let me again emphasize that sometimes they break accidental symmetries, and then the effect of the standard model is 0. So they are not a small correction to the standard model. They can be the leading term if they break an accidental symmetry of the standard model. They are small, but not smaller than the standard model. And since they are small, if we want to notice them, to know that they contribute to understand their effect, then they compete with standard model loop correction. So far, everything that we did is so-called tree-level contributions. We did not go to loops because loops are suppressed, because this was the simplest and because I wanted to emphasize the main features of the standard model. But if we want to look at this, then we have also to calculate the loop corrections. Until now, we only did the normalizable terms and tree-level, and from here on, we will use the standard model effective field theory. So we will look at non-normalizable terms, and we'll also sometimes have to look at loop contributions of the standard model itself, whether they compete with that. And there are three main classes, or three main directions of experiment or programs that aim to find the effects of such non-normalizable terms. So the cleanest of this, one where when we see effect, we know it's new physics, are of processes that are forbidden within the renormalizable Lagrangian of the standard model. So that's related to the accidental symmetries of the standard model, and such processes can be violated or can occur due to non-normalizable terms, but not by loop correction. So for these, neutrino masses, proton decay, we don't have to calculate the loops because the accidental symmetry tells us that the process is forbidden to all orders in perturbation theory. That's the power of accidental symmetries. And the two leading examples are neutrino masses and mixing and proton decay, which are searched for. There are additional things. There is something called neutron, anti-neutron oscillations, and perhaps other ways. Yeah, mu to E gamma, a list of things that are forbidden by this U1 to the 4 symmetry. U1 baryon number, U1 electron number, U1 muon number, U1 tau number. Then we can use rare processes, processes that are not allowed in the renormalizable standard model at tree level. In most cases, it's because there is an accidental symmetry not of the entire standard model, but of a sector of it, and then the processes within this sector at leading order do not occur. But because they are not symmetries of the entire renormalizable standard model, they will be generated at the loops. So if we see a deviation from the standard model renormalizable tree-level prediction, we should both understand how much loops contribute and how much room there is for non-normalizable terms. And the main program that goes along this type is measurements of flavor changing neutral current processes, which occupies about 2 chapters in this whole program, but I will skip it. You are welcome to read the relevant chapter in the slides. Yeah, maybe I just mention, first of all, there are quite a few dedicated experiments that take part in this program. Babar and Bell were such experiments, LHCb and Bell 2 are known. And this program, even before the full spectrum of the standard model was discovered directly, allowed us to make interesting predictions. So at least 3 parameters of the standard model have been discovered via such processes before the particles themselves were discovered. So the charm mass, the mass of the charm quark, was discovered via such process well before the charm was discovered and was predicted correctly. The top mass was understood what it's be by these processes well before the top was discovered in 95 directly in Fermilab. And the Higgs mass we could tell from such processes, not only from such processes, but also. So, forbidden processes that in the standard model, the normalizable one at tree level, do not occur at tree level, but only at the loop level. and even processes that in the standard model occur at tree level. It could be that a particular sector of the standard model depends on a small subset of parameters, and therefore there are relations between various processes occurring in that sector. And these relations are violated both by loop corrections that bring in the other sectors of the standard model and possibly by non-normalizable terms. So again, you have to know both. And here there has been a very rich program, one for which we learned a lot, called electroweak precision measurements. This was carried out by the LEP experiments in CERN, SLD experiment in SLAC, and it's now more or less the program hoping to find new physics of Higgs decays. And of these various directions, I will today and tomorrow describe two. I will discuss neutrino masses, and before that I will discuss Higgs decays. The choice of Higgs decays is because this is the main program of Atlas and CMS. It's much interest now to theorists. The program only began in 2012 because that's the time that the Higgs was discovered and we could start measuring its decay rates. So I'll say what has been measured, how it tests the standard model, what we know, what we don't yet know, and then perhaps the most interesting of all, because that's neutrino masses, is the program that tells us that the standard model, it's the one that found beyond the standard model physics. Yeah, that I mentioned. So before all standard model particles were directly discovered and all the standard model parameters measured, which is the situation now. We have all the spectrum of the standard model has been directly produced. All the parameters, we said there are 18 parameters, we know all of them. So before that, we could assume the validity of the renormalizable standard model. And through such program, we could measure the properties of particles that we have not yet observed and predict them. So that was the Char mass, the top mass, and the Higgs mass, which were known before, or predicted before these particles were discovered. Now we know everything about the renormalizable standard model. We've seen, everything is a big word, but we've seen all the particles. Sorry. And we measured all the parameters. So now we can calculate all the loop corrections, and we can unambiguously know whether the measurement has room for non-normalizable terms or requires non-normalizable terms or not. And now all these classes of searching for new physics that I presented on the previous transparency can serve the search for beyond standard model physics. So we will go to our first example of how this is done in Higgs decays. The red bar is dangerously going down. Yeah, there will be even something beyond the final transparency or something. But yeah, so we are still, we'll skip that and go from here to neutrinos. And if time allows, the cosmological tests, which I think are fun to understand how particle physics, the physics of the smallest, and cosmology, the physics of the biggest, how they talk with each other, these programs. Even philosophically, it's interesting. Okay. So I gave these 3 examples, and we are now here. Things that occur in the renormalizable standard model at tree level and could be violated by loops or by non-normalizable terms. And we can calculate the loops because we know all the parameters and hope to find deviations from the standard model predictions. So the Higgs decays have quite a few special features in the standard model. It's really a set of predictions that is very strong. So I'll first present what are these features. Then I'll show the present test or the measurements that are relevant to test these features, what we know and what we don't know. And then we'll see the example of non-renormalizable terms in the standard model effective field theory that are being probed by these measurements. It's a short chapter, I think, so we'll see. Maybe we'll start neutrino masses today. So here are 4 features you can separate. So essentially, when we presented the Yukawa interactions, we said we can present them as these Yukawa couplings, or we can present each of them as the mass of the particle times square root of 2 over V. Now this relation, I should write it, will make our life easier. So in the renormalizable standard model, the Yukawa of fermion I equals square root of 2 mi over V. Okay, that's it. And I now argue that there are 4 features in this simple formula, not just one. It has a lot of content. So here it is. First of all, the relation between 2 Yukawa couplings is the same as the relation between their masses, the ratio. That's proportionality. It tells us that if we have a plane of the Yukawas versus the mass, it should lie on a straight line along this. Right? That's what this first thing. But it does more than that. It tells us what is the factor of proportionality. So it tells us the slope of this, not just telling us straight line, but tells us the slope of that line, and that's yi over mi is square root of 2 over v. That's also here. The third thing, there are no off-diagonal couplings. There is no Yukawa couplings of the Higgs to a bottom and anti-strange, to tau plus mu minus. Only diagonal couplings. So that's the third feature. And the fourth is that it is CP conserving. What would signal CP violation in this context if in the basis where the mass is real, the Yukawa is complex. Okay, so it's a relative phase between the Yukawa coupling and the mass. We almost always use basis where the masses are real, and so that translates the CP violation is a complex Yukawa. But it's important to emphasize, it seems almost trivial, this statement, but when we add terms of non-normalizable terms, then we should be careful to go back to the basis of real mass, because it could be that the higher order terms give the mass that was at the renormalizable level real, take it away from that, and we have to rotate back to the basis where the masses are real and understand if the Yukawas are complex there or not. So these are the 4 features, and each of these has been tested to some extent by Atlas and CMS. So let us see where we stand now with this test. And of course, violation of any of these is almost clearly a signal of new physics. It could also, loop corrections can take us away from this, but most of the loop corrections that violate these are proportional to the Yukawa themselves, and except for the top, all the Yukawas are small, so the loop corrections are very small usually, and this should be respected at a high level. It's written here. Why did I say it before? Okay. So that's the program of the Higgs program and how it is tested. So this is what we know in blue about Yukawa coupling, and why this is separated I'll say in a minute. And in light blue, what we know about the coupling of the Higgs to the vector bosons, because that will also appear on the plot that Atlas and CMS provide us, and because the standard model has also a prediction for that. So first let me tell you what mu is. You produce the Higgs in some process, and then the Higgs decays to a final state, for example, BB bar. And the ratio between this production and decay into BB bar, or the rate of these experiments normalize it to the standard model prediction. So mu is the ratio between, it's here, the chalk, the production of the H times the branching ratio of H, let's say to FF bar, that would be mu FF bar, versus the same thing as here, the theoretical value in the standard model. That's what's written here. So one is exactly the standard model, and then there are uncertainties. So what we know about, and also when interpreting it as Yukawa couplings, we are assuming for these that the production process, which has to do with gluons, is as in the standard model. So it's a subtlety, but let us not dwell on it too much. So this is what we know. For BB bar, very nice, close to the standard model, tau plus tau minus, within 1 sigma the standard model, mu plus mu minus, within 1 sigma the standard model, CC bar, something like close to 2 sigma from the standard model, but still very low statistic. You see here the very large uncertainties, and at least from my experience, when you have low statistics, many times you have large deviations which then shrink down, but still 2 sigma, it's not very significant, and I wish it will remain away from the standard model, but I suspect that it will converge as the errors go down. The Yukawa of the top is known not from the decay, because the Higgs cannot decay to TT bar, the top is too heavy for that, but from the production of T bar H, because we think it's coming in the LHC. Can you see there when I write here? From 2 gluons becoming T and T bar, that's also T, and emitting H. That's the leading contribution. And so here, there is the Yukawa of the top. So it's a different process from the other. It's not the decay, it's the production, but also consistent with the standard model within 1 sigma, and give us constraint on the top Yukawa. And then we have here WW star, which I explain what it is, ZZ star, gamma gamma, as I mentioned, the production mode, and I think, still the most precise mu, and the very recent Z gamma, again 2 sigma, but still very low statistics. So this tells us something about where the Yukawas are, what are their values. So each of these, if you want, is the ratio of the Yukawa as measured to the standard model Yukawa squared. So they should sit on a straight line whose slope we know from the standard model. Does it or doesn't it? Well, the fact that all of them are more or less consistent with 1 tells us that it will be, but let's see how it looks. So these are CMS and Atlas, each presenting their results. So what I gave before is the average over them. This is a logarithmic scale. So here we have, this is CMS, the particle mass in units of GeV, starting from about 100 MeV, which is the mass of the muon is a little bit heavier than that, ending at a few hundreds GeV or 200 GeV. The top is 173 GeV. So that's the range of the things that have been measured. And we see here, this is the straight line predicted by the standard model with the slope predicted by the standard model, the top, the Z, the W, the bottom, the tau, and the mu. So not bad at all, I would say. Here it's here it's normalized to the standard model value. So everything is consistent with the standard model. And you see here clearly that the Yukawas are proportional to the mass, which is a general feature. You see here clearly that proportionality and the factor of proportionality are confirmed by experiment. We hoped that this will not be the case. And even when we understood that for the Z, the W, and the bottom, and later the tau, it happens, we said, okay, maybe third generation, yes, but second generation, no. But then came the measurement of the muon Yukawa, and also second generation is there. So it's not only confirming the standard model prediction, it's really telling us a sentence that I repeated already several times, because I think it's a significant sentence. It tells us that all of these particles that are written here, the dominant source of their masses is their interaction with the field related to the particle that was discovered. Okay, why the Yukawa is the interaction with the particle? The mass, is the interaction with the field. And if the field is the one that is related to this particle, then in general, this line should be there. Okay, so it's something more abstract or deeper than just the standard model. This is the Atlas measurement, top C, W, bottom tau, mu. They even, well, for them there is only a low upper bound on the charm. CMS did not want to put the charm because the errors are large, or perhaps it was before. This is in 2021, I don't remember exactly. Yeah, so no, 2022. These two plots were made for special papers by each of these collaboration, celebrating 10 years for the discovery. And so it was like the Higgs after 10 years, and it was one after the other, these two papers in the Nature magazine, where particle physicists tend not to put their papers, and rightly so. We have our professional papers. We don't want to pay the journal for it, and we don't like Nature and Science and the particle physicist, okay? It's kind of a proud thing not to publish there, unlike life sciences and many other disciplines. But this is a special celebration, so still there, and we see the first two features that I wrote before, proportionality and the factor of proportionality, so far well consistent with experiment. Oops, the wrong direction. Diagonality. So these are the searches for off-diagonal couplings. There are only 5 off-diagonal couplings that one can explore, at least at present, and it may be, I don't know, forever, experimentally. So the 3 off-diagonal couplings in the charged leptons. Charged leptons are easier experimentally than quarks. We know well the E, the mu, identify them very well. The tau is a bit more complicated to identify, but still rather cleanly this. So There are only upper bounds. We have not observed any non-diagonal decay at the level of few times 10 to the minus 5. That's very strong on the mu, and few times 10 to the minus 3 on the tau and E or tau and mu. And then you can explore off-diagonal couplings in the up sector, but not in Higgs decays in this case, but by top decays. So a Yukawa coupling to a top and a U, or Yukawa coupling to a top and a charm would give these decay modes for the top, and the bounds are all there 10 to the minus 4. So how to think about it? Better think of what they tell us about the off-diagonal relation to the corresponding diagonal coupling. So even though the branching ratio of H to E mu was a very strong bound, the ratio with the diagonal Y mu is only at present constrained to be smaller than about a half, and Y E tau and Y mu tau are about a factor of 6, 7 at most, smaller than the Yukawa of the tau. A somewhat stronger bounds on the off-diagonal couplings in the up sector compared to the Yukawa of the top, 0.02, 0.03, so that's where we stand. Each of these can be translated to a constraint in the standard model effective field theory. So now just telling what are the numerics of the constraint and what has been tested and through which processes. And finally, we said it should be CP conserving. And in a sense, these numbers, so there are only two ways more or less, or two Yukawa couplings which experiments know how to explore the possibility that they have an imaginary part. So these numbers here refer roughly to the imaginary part of the tau Yukawa compared to the real part, and the imaginary part of the top Yukawa compared to its real part. So definitely consistent with no CP violation. So it translates into roughly these things. The relative phase between the Yukawa of the top and the real standard model Yukawa coupling is smaller than 30% and similar for the tau. So this is what we know. There is no violation of any of the four features. The program goes on, accuracy will become better. Maybe we will have the Yukawa of the charm with more accuracy. By the way, there are additional things. For example, there is a search for Higgs go to E plus E minus. Now remember, the Yukawa of the electron is extremely small. If it's the standard model value, the hadron colliders at least will never be able to measure it. So you should not be surprised that the bound sounds like weak. So U, E plus, E minus, which I did not present here because cannot, so I presented tau tau and mu mu. For EE, the upper bound is 670, I think. Okay, so see, these are numbers of order 1, but the electron, no, it's 200 times roughly lighter than the muon. It means that the Higgs branching ratio into electrons is 200 squared, 40,000, I think, smaller than its branching ratio into mu plus mu minus. So it's a tiny branching ratio, and 670 times that, it may be not such a bad achievement by the experiments, but I'm afraid that we will never be able to put the first generation Yukawa on plots with experimental data points. There will be upper bound, but the upper bound will be almost meaningless as a test. Unless, of course, we discover that it's much larger than the standard model. So how do we translate this into constraints on new physics? The nicest thing would be to see a violation of standard model prediction and then interpret it as new physics would be a lot of fun. Here it's just putting constraints, so I'm demonstrating how theorists put constraints. The details are not very important. So this violation of the relation between Yukawa couplings and masses, that's our main tool. Okay, the Yukawas are proportional to mass. We know the proportionality factor, and we know that it's Yukawa is real in the basis where the mass is real. So violations of these, also of diagonality, come at dimension 6. Actually, take any standard model dimension 4 term and add to it phi dagger phi. That is one of the dimension 6 operators of the standard model effective field theory. Right? Because the dimension 4 terms are like the Yukawa terms, like the Higgs quartic coupling, like couplings of two vector bosons and two Higgs fields, etc. We know that they are made out of standard model fields and they are singlets of the standard model gauge group. That's how we derive them. And phi dagger phi is made out of standard model fields and is a singlet of the standard model gauge group. So among the many terms that are allowed at dimension 6, there are all the standard model dimension 4 terms with the addition of phi dagger phi. So in particular, there are the combinations that make the Yukawa couplings, phi with a left-handed bar f right or f right bar f left, add to it phi dagger phi. These are terms that are part of the standard model effective field theory, products of standard model gauge group, products of standard model fields, singlet of the gauge group, in dimension 6, 1 plus 1 plus 3 halves plus 1 plus 3 halves, that's 6. So they have coefficients which are proportional to high energy scale squared. Now, it's convenient, it's a little bit complicated what you see. So you see, they will contribute to the Yukawa couplings when you replace two of these three phi fields by the vacuum expectation value. Right? So you have a contribution to the Yukawa which is proportional to v squared over lambda squared, the ratio of these two scales squared. They contribute to the mass when all three of them are replaced by the vacuum expectation value. So there is a contribution to the mass, there is a contribution to the Yukawa, and the ratio between these additional contributions to the mass and the Yukawa do not obey the standard model relations that I wrote before. They are different. For example, just for the Yukawas, you can replace any two of the three with the vacuum expectation values. So there are three possibilities. You can leave this phi and put v in these two. You can leave this phi as it is and put v in these two, or you leave this phi and replace these two with the vacuum expectation value. So there are three possibilities. For the mass, there is only one possibility. You have to replace all three with the vacuum expectation value. So already there is a factor of 1 to 3 that is not something that happens when you go from the Yukawa matrix to the mass matrix in the renormalizable terms, where it's just one possibility. So in general, the contributions to the Yukawa are suppressed by v squared over lambda squared, and standard model contribution to a diagonal coupling is the Yukawa coupling of the renormalizable term. So this is roughly the ratio between the real part of the new contribution and the standard model part to the Yukawa, and this is the imaginary part. So TR and TI are the contributions, dimension 6, roughly normalized to the standard model value. So first of all, in the standard model, y over the mass squared was 2 over v squared. It's written actually here. Y over the mass squared is 2 over v squared. Here there are corrections to that. corrections related to the dimension 6 terms. There is also CP violation coming out of there. So imaginary of m times the conjugate of the Yukawa, which in the standard model is 0, because in the best basis the Yukawa is also real. Here it's not. It must be proportional to Ti. If this does not have a phase in it, then CP will not be violated. So you have that. And so the constraints on the Higgs decays to pairs of fermion translate into constraints on this Tr and Ti, and similar on the CP violation, and similar, I did not write it, on the off-diagonality. So here, perhaps the clearest contribution thing, this is what is allowed by the current measurement of Higgs to mu mu. The current measurement of the Higgs to mu mu tell us a range for the Yukawa, and so it translates into a range, allowed range, how much room there is for Tr and Ti. The point 0, 0 is within the allowed range because the measurement is consistent with standard model, and we see that the ratio can be perhaps, Tr can be as large as 0.5. So let me take you back just to understand what is happening. So Tr can be as large, for the muon, can be as large as 0.5. The Yukawa of the muon, which appears here, so let's take this to the left side. The Yukawa of the muon is about 6 times 10 to the minus 4. Multiply it by 0.5, it's 3 times 10 to the minus 4. And that's roughly the upper bound on v squared over lambda squared, which translate into a lower bound on the scale lambda, which is around 10 TeV. So, and similarly, here is for the tau and for the bottom. I will not go into details. All of them explore scales up to 10 TeV. In other words, the present accuracy is sensitive to contributions of dimension 6 terms of the form that I showed, Yukawa terms times phi dagger phi, if the scale is up to about 10 TeV. If the scale that suppresses it is much higher, then we are not yet sensitive to it. If it's below 10 TeV, we could have observed it, and we did not. So that's the kind of thing that is being explored, and how it translates into constraints on the non-normalizable terms and a lower bound on the scale as long as we do not observe new physics. Once we observe deviation from standard model, we will have the much more interesting case of an upper bound on the scale of new physics, and that will be the case with neutrinos. So, still a lot of time, and we are done with Higgs decays. So we go next, we go to neutrino masses.
So what is that X?
Yeah, it should have been, X should have been, I think, C. I think it's this C, but I'll check it later. But I think just
That's dimensionless.
Yeah, the C is dimensionless also. The dimensions are in the 1 over lambda squared here. But I'll check that what I'm saying is correct. Yes.
You said that
It's okay.
So you said that experimentally it is verified that top, bottom and muon mass is come from the standard model Higgs.
Top, bottom,
Most of their contribution.
tau and muon are all dominated by the interaction with the Higgs field. Yes.
Okay. Then isn't it automatically rule out the type 2 Higgs doublet model, where the up type and down type actually coupled to the different type of Higgs doublet? Because
yeah, it's a good question. So I didn't mention it, but actually it's think it's an interesting fact. So, if you see deviations from these four, you may be able to see deviations from some and not deviations from other. So just as an example, there is a 2x doublet model with natural flavor conservation. That's some extension of the standard model. And in that, the proportionality is maintained, but the factor of proportionality is different, and it's different for each sector. So it's one proportionality factor in the, in the 2x doublet model, actually, two sectors have the same proportionality factor, not as in the standard model, the same with each other, and another sector has a different proportionality factor. And perhaps the most popular of these is the 2x doublet model type 2, okay, because it's most popular because the supersymmetric standard model has this type of scalar sector, and then the proportionality factor of the down and charged lepton sector is 1, it's called usually tangent beta, and in the up sector it's different. So the fact that we have evidence that the proportionality factor in all three sectors is the same, and also the same as in the standard model. So it would be the same in 2x doublet model type 1,
Okay. Yes.
but to be the same as in the standard model is kind of surprising. So it's automatic if the second Higgs doublet that you add is very heavy. Then it becomes closer and closer to the standard model. So in a sense, it puts a lower bound on the mass scale of the second Higgs doublet, and that could probably be around 10 TeV, or that there is a miracle, what's called tangent beta equal 1. 2x doublet model type 1 with tangent beta equal 1 would also give there. So there are ways out. It doesn't exclude multi-Higgs doublet models, but the effect in these models could be huge. You could have the proportionality factor deviate from the standard model by a factor of 90. Okay, tangent beta equal 90 was legitimate. Definitely 10, 5, and it's very close to 1 compared to the standard model. So maybe 2x doublet models are there. If they are not, the second Higgs doublet is not very heavy, 10 TeV or more, then it's a bizarre accident that it mimics the standard model. I cannot say it's excluded, I can only say that it's strange that it decided to cheat us and give us the appearance of the standard model when it is not. But the model can do that. Yes?
A question on slide 15.
Yeah.
Yeah, so we see that ratio, right? YT divided by under root 2 MT by V. So I think that maybe the
see
mass
that
term
square root should not be on the MT,
Yeah.
and you are right. Absolutely.
radical is 2.
This is a typo, okay? Sometimes I make mistakes that are physics mistakes. This is a typo, yeah. Cannot be that, this is dimensionless, and as it stands in dimension full. It's something that should not happen to physicists, but yeah, typo. Should put the curly bracket on the 2 and not on the MT. I'll fix it. Thank you.
Basically, DSM contains the standard model.
This?
Thank you for this talk. Basically, BSM contains the standard model. Standard model has some parameters that we have discussed already. BSM also has some parameters. They are the fixed by the standard model, or that can be any number of parameters, or there is some constraint.
I'm not sure I understand the question. So there are new parameters in the BSM model, and
My question is that there is a limit on the on the parameters of the BSM,
Yes.
and the number of parameters is fixed by the SM, or something is depend on the what we want to look for.
So the number of parameters, in principle, grows very quickly when you add non-normalizable terms. Here we are doing with dimension 6. Those that affect the Yukawas and the masses are those, in what I showed, are this type. So these are 3 by 3 complex matrices. So we have here 3 by 3 is 9 plus 9, 27 real and 27 imaginary parameters that go beyond the standard model. So yeah, we have here 27 new parameters, and with y mu, I constrained 2 of these 27, and the constraint is actually what's written here.
Okay.
Okay,
Thank you.
I hope I answered the question because I'm not sure.
There is no BSM model which reduces the number of parameters.
Ah, that was the question? Okay, I didn't answer at all. No, I'm not, okay. Within the quantum field theory extensions of the standard model that I'm aware of, there is no model that reduces the number of standard model parameters. And some people, and sometimes, I don't know if it amuses me or irritates me the way it is presented. For example, grand unification. Okay, you say, I take the 3 couplings, gauge coupling on the standard model, and I replace them with 1 coupling, so I reduce the number of parameters. However, to achieve the spontaneous breaking that is needed in grand unified theories, you have to introduce a rather extended scalar sector, which I guess has tens of new parameters in the scalar sector. And so the overall number of parameters in grand unified theories is much larger than in the standard model. The supersymmetric standard model has 124 parameters, most related to soft breaking of the supersymmetry. 2x doublet model has in the scalar sector, if I remember correctly, 7 quartic couplings and 3 quadratic couplings compared to 1 and 1 in the standard model. So almost any extension, it's not just a small increase in the number of parameters, but a big one. So I think there is a community that would like to aim at models that have much fewer parameters in the standard model, ideally to 1 or 0 parameters. And I think at some period, there was hope the string theory would do that it has 1 fundamental parameter. However, first of all, it turned out that there are many, many infinite number of different string theories, but also, while perhaps they have a single fundamental parameter, the string tension, when you go down in energies to reach the phenomenology, when the effective field theory of the string theory, there are many more parameters, and in any case, so far string theory did not manage to provide a predictive model that can be tested, so I don't think it can be considered at present. But one could hope. Oh, maybe one day someone will discover something new and sophisticated, where originally you will have 1, or as I said, even 0, and so everything will be emergent. Somehow the dynamics along the way would give you all of these parameters, and it would even tell you their values. Maybe, but it's definitely beyond what we can do now. So I'd say any quantum field theory, PSM, that I'm aware of, increases significantly the number of parameters. Okay.
Any more questions? You had a question in the last lecture. Want to ask?
So I have a question from the last slide.
From the
Last chapter. Sorry, last chapter.
Previous chapter.
Yeah, previous chapter, chapter 11. So in one of slide you mentioned that in case of fine tuning, parameters which requires accidental fine tuning cancellation. So what is the meaning of that?
Okay, so let's say that the cutoff scale of the standard model is the Planck scale. Then, related to the fact that the Higgs mass squared has, from the loop corrections, I have a better answer. Okay. This is an answer that convinces me about the fact that the Higgs mass is fine-tuned, which, as long as the argument included the Planck scale, I personally was not convinced. However, we discovered neutrino masses, see tomorrow, and the most plausible explanation requires that there is a fermion, right-hand fermion, that is a singlet of the standard model, and that it has Yukawa coupling with the standard model. And that if the Yukawa is of order 1, then its mass should be of order 10 to the 15 GeV. So that gives a correction to the Higgs mass by a loop Higgs, the neutrinos that we know and love, and this new thing. In the seesaw models,
What is the NR?
NR is the new field, which is 1, 1, 0 in the standard model gauge group, and which is required in seesaw models and in others to give mass. So the Yukawa must be there in these models that explain, the simplest models that explain neutrino masses. This must be there with a mass of 10 to the 15 GeV. And this contribution from loop to the Higgs mass is of order the Yukawa, let's call it yn squared times the mass of the Higgs squared is this squared from the loop, which is about 130 GeV squared. This is a finite contribution, okay, unlike the ones that we are talking about. But the Higgs mass the physical Higgs mass, we've measured it, mh squared is 125, so the square is GeV squared, which in physics is 10 to the 4 GeV squared. Physics, I mean 25 is not important. So this is the physical, okay? This is what we measure. So mh squared physical equals mh squared at the tree level plus this loop correction. Let's call it mh squared n to remind us that it comes with such a loop. And so you need this, which you don't know because you just measured that. This is an unknown parameter. This I just more or less calculated. They need to cancel each other to 26 significant digits to get from 10 to the 30 to 10 to the 4. That's the fine tuning.
Okay.
These two parameters have to cancel to 26 significant digits, which I find unfair if nature does that. Okay, cheating us somehow. It's not. I'm saying it's not impossible. That's what nature decided to do. Choose two completely different parameters. This has to do with Yukawa's, with the mass of this thing, which is a Majorana mass. Okay, so it's a parameter. All of these here are parameters in the Lagrangian. That is also more or less a parameter in the Lagrangian. They are independent of each other, and nature decided to make them say equal to 26 significant digits and differ at the 27th. Surprising, very surprising, unlikely, but could be also related to the way that we calculate physics. So I should be cautious about that. But this is the situation, that's what fine-tuning is.
If possible, could you please open the last chapter and then go on that slide, which represents the plot of events?
The what?
So if possible, could you please go on the last chapter and go on that slide, which represents the plot of events for neutrinos?
The plot of?
Neutrinos. Event plot of neutrinos in the last chapter. In the previous one.
In the previous one on neutrinos.
Yeah.
I will discuss now neutrino physics, so it will not be there.
No, it's related to solar neutrino on that slide, and then just after that.
Okay. Installing update. Aha.
So fine.
So,
Actually,
okay. Should I open it?
Actually, Adobe is not working. It's updating.
Oh my god.
You can open in the other app.
This one is opening. What is the? This is the other file.
Which chapter is this?
Chapter 11.
No, this is QCD. Not what we want. Yes.
In this one. So what is on the x-axis in the probability expression?
Here?
Yeah.
Here? This is the energy of the neutrinos in MeV.
Okay.
Yeah, it's cut out the scale here, but this is the energy, and actually it's an interesting thing because the sun does something very nice for us. There are two types of neutrino flavor transition. One is vacuum oscillations. That's the thing we always learn first when we study about neutrinos. And the other is something called the MSW effect, something that happens neutrinos when they go not in the vacuum, but in matter. The sun has planned its density and the neutrino parameters, or whoever designed them, so that we have the two phenomena for us. This is about the transition. What we see here, which is most of what has been measured, particularly in the beginning, above MEV, so the Homestake experiment, the GALEX, all other have been there. That's the MSW effect dominated. And below this, it's vacuum oscillations that is dominant. This probability in the limit of pure MSW or pure neutrinos. So for pure MSW, it's something called sinus square theta. It's the mixing angle between the electron neutrino and spin. And here it's 1 minus half of sinus square 2 theta. And it should be consistent with the same theta, and it is. And it's beautiful of the sun to give us. And actually, the first measurements of these are all of the MSW effect, which is, I mean, people think it's vacuum oscillations, but the first measurements are all of the MSW effect. So that's what we see here. That's why we have two different values and transition. So we are able to measure the solar neutrino spectrum over this range of energies, and this is what we see.
So in general, we study standard oscillation between different flavors of neutrinos, or I can say different mass eigenstate. So is there any way?
No, between flavors. So, yeah.
No, not mass. So is there any way to suppress this standard oscillation between different flavors, and instead of that, to study the oscillation between different helicity state?
So
Possibly, till now we know.
Yeah, so I think there was a possibility that what we observe is spin per session. So I guess the answer in principle is yes. This is not what is happening with the solar and atmospheric neutrinos, but it could be. I think that's called, yes, spin per session, and was suggested in the beginning as one of the possible explanation of the solar neutrino problem. But I do not remember now enough details of that to give detailed answers.
Okay, thank you, sir.
Okay, we have 10 minutes. I'll start neutrino masses if that's okay, even though it's 10 minutes, because we have only tomorrow after that, 2 hours. So let's see. Used. Yeah, 14. Okay, getting closer to the bottom with the red. So neutrinos. It's very good that we have neutrinos. Okay, each time they surprise us. Wonder what's the next thing. Yeah, so I gave already this. Now we are in experiments that look for effects that should not occur according to the accidental symmetries of the standard model. So we don't need to worry about loops. We just need to see what's happening. Let me skip. Yeah. So for neutrino masses, it's not there at tree level, it's not there at the loop level because it's protected by an accidental symmetry. If not observed, it's a lower bound on some scale. If observed, there is no question that's evidence for beyond the standard model physics, beyond the standard model as I defined it, okay? Because some other people tend to modify the definition of the standard model according to what is observed, and that's confusing. If observed, there is an upper bound on the scale of new physics involved. So we said this is the accidental symmetry. Its violations of it are searched for in decays like mu to E gamma, tau to mu minus mu plus mu minus, z to, let's say, tau minus E plus, etc., and has not been observed in any of these charged lepton decays. And yet, lepton flavor violation of these symmetries has been established in neutrino oscillation experiment. So in all of these neutrino oscillations, you have a source that produces one of the flavor states, so either Ni or Ni mu or Ni tau. You put a detector far away from that, and you observe a neutrino of a different thing. So you produce electron neutrino, and you observe mu neutrino, or you produce mu neutrino, and you observe tau neutrino at a distance. Or some of the experiments, you produce electron neutrino and you observe fewer neutrinos, electron neutrinos than you should have at the distance. So appearance experiments are those that search for a different type than the one that was produced. Disappearance experiments are the ones that look for a smaller flux of the original one. So transition produced mu and observed ni tau has been established by the atmospheric neutrinos. Transition from electron neutrinos to muon and tau neutrinos have been established for solar neutrinos, and all of these and more have been confirmed by accelerator and reactor experiments. So lepton flavor violation is by now well established. These symmetries are broken in nature. Lepton number violation, a subgroup of this, the sum of these, so the sum of electron number, mu number, tau number, number of leptons minus antileptons has not been experimentally established. It is searched for in a very peculiar type of experiment called neutrinoless double beta decay, but not observed yet. So if it will be observed, it will make the idea that these are Majorana particles, we give a very strong support for that. As long as we do not observe them, I'm still convinced that they are Majorana neutrinos for reasons that I will make clear soon, but it's not established experimentally. So there is a long program, and so we know that there are neutrino masses, and it's not really a model now, but I'll go along the same method that I did so far. Define a model, find the spectrum, the interactions, symmetries, parameters, and more. So the definition of the model is the same as the standard model. The only thing, so this is a name that we gave this model. The only thing is that we now say we go up to dimension 5, okay, for the next dimension. So it's part of the standard model effective field theory. It's the first addition that you make to the renormalizable standard model. So it's really not another model, but let's see, because it have, so just a definition now of what I mean. So the Lagrangian is the standard model, the renormalizable standard model Lagrangian, and the only type of dimension 5 terms that is allowed is this: 2 scalar fields and 2 lepton doublet fields. Okay, so it's 9 terms. It's a 3 by 3 matrix here, symmetric. Yeah. And it's suppressed by 1 over the scale plus Hermitian conjugate. So this Z here, symmetric, complex 3 by 3 matrix, dimensionless couplings. I took the dimension into explicit lambda, and lambda is a high energy scale, which by definition, we are doing here non-normalizable terms, must be much larger than the electroweak scale. So what would be the consequences of adding this? That's okay. We defined the model, we found the Lagrangian. That was quick, I know, but we did it because it's a simple extension of the standard model. And the first thing it has an effect on is the neutrino spectrum. So the only thing that can get vacuum expectation value is the field phi. If you want masses, you need to replace both phi's with the vacuum expectation value, and you discover that this become mass terms for neutrinos and neutrinos only, even though in the L itself there are also the charged leptons. But when you do the contraction with the lower component of the phi's in the right way, you'll get neutrino masses. So it's still, the mass matrix is the matrix Z, and the 2 phi's become V squared over 2. So we have neutrino masses, okay? And this is the mass matrix. And this is an entry in that. And as before, we can bring this mass matrix into a diagonal and real form by a unitary transformation. So far, we always needed B-unitary transformation, but this is not the most general 3 by 3 matrix, it's symmetric. And if it's symmetric, then it's the same, it's the matrix and it's transposed on the 2 sides. It's not 2 independent matrices, That's enough to bring it to diagonal form, and we give the diagonal entries the very disappointing, non-creative names of M1, M2, M3. I mean, we were really full of creativity, top, charm, strange, bottom, all these 9. Electron, muon, tau, I have no idea where they come. And then these masses, and we call them M1, M2, M3. How? I mean, we should improve. We should not go back on our creativity. But that's the name given. And we gave the neutrino mass eigenstates, those with these masses, the names neutrino 1, neutrino 2, neutrino 3. Either we would have done it with everything, U1, U2, U3, or everywhere we give names. I don't know what happened to the community. And so, in the top charm and up, in the tau, mu, and electron, we always define the states by the order of the masses. We gave a name to the heaviest, we gave a name to the lightest, we gave a name to the one in the middle. That was the definition of what we mean by mass. Here, we went a different way, because actually we don't know which is the heaviest of them. So, don't know, we changed the convention, we still want to define what they are. So there are mass square differences between 3 masses. There is m3 squared minus m2 squared or 1 squared. And by convention, delta m squared 3, 1 or 2 is the largest. It's largest than delta m squared to 1. But we don't know if it's positive or negative because experiments have not told us. That's where our ignorance about which is the heaviest lies. And in delta m squared 2, 1, we know that one is heavier than the other, so Ni1 and Ni2 are the ones separated by the smallest delta m squared, that's the definition, and M2 is heavier than M1. So just to say why this doesn't, why we don't know. So in the picture, which I think is clear, we have 2 and 1, 2 heavier in 1, so y-axis is mass, and 3 could be here or could be here. All we know is that its splitting for these two is larger than this splitting, but we don't know whether it's above or below, so we change the way we define the conventions. And here is what we know experimentally. So this is the spectrum, 3 massive neutrinos, and we know only mass squared differences. So the small one is about 8 times 10 to the minus 5 electron volt squared, and the big one, small but bigger than this, is about 2.5 times 10 to the minus 3 electron volt squared. That's what these measurements tell us. So that's the spectrum. It's something like either that or that, mass squared splitting 8 times 10 to the minus 5 EV squared, mass squared splitting 2.5 times 10 to the minus 3 EV squared. That's the experimental information. We still don't know the absolute mass scale of the neutrinos. They could all be much heavier than the square root of the mass squared difference, okay? And then they are very degenerate, or they could be completely hierarchical with the lightest even 0. It could be that this has 0 mass, or if this is here, 3 is here, it could be that 1 is massless. Still, that's the most hierarchical case. So that's, we don't know. And also we don't know the mass ordering. We don't know if 3 is the lightest or the heaviest. So these are, but still, actually, when we say we don't know the absolute mass scale, we are exaggerating. We are too modest. We know quite a lot. So if you have a mass squared difference, there is at least one neutrino that has a mass larger or equal to the square root of this mass. So there must be at least one neutrino that is heavier than 0.05 electron volt. And given the other mass square difference, there must be another that is at least as heavy as 0.009 electron volt. So we have lower bounds on 2 of the 3. So that one could be massless, but for 2 we know. And from other experiments, searching for neutrino masses, in particular now the Katrin experiment in Germany, we have an upper bound of about 0.8 electron volt. So I would say that within a factor of 16, we know one of the masses, okay? So it's not that we completely don't know where the mass scale is, but that's thanks to direct searches, and it's improving all the time. So that's what we know. And as you can see here, soon stop, so just finish with the spectrum. The mass is of order v squared over lambda, okay? We write just times z1, z2, and z3 after we diagonalize. But the overall scale is v squared over lambda. So we know that all the neutrinos are much lighter than the electroweak scale. So, and the z scale is the, yeah. So it makes sense, they are small, it makes sense that they come from higher dimension terms. But I think what is even more impressive is that there are quite a few fermions that are lighter than V. Scale of mz and mw, v, except m top, all of them are much lighter. But the neutrinos are much, much lighter. In fact, there are 6 orders of magnitude at least lighter than any of the charged fermions. So the fact that here we have an explanation for that, because the scale of all the charged fermions is v, and the scale of the neutrinos is v squared over lambda, so it's suppressed by v over lambda compared to the scale of the charged fermions. That's, I think, for me, it's an explanation, okay, of why neutrinos are much lighter. Here there is also something that some people argue, say, okay, the electron is 6 orders of magnitude lighter than the top. So why do you think that if neutrinos are 6 orders of magnitude lighter than the electron, it's a different mechanism necessarily? And my intuition or answer is, within a generation, the hierarchy is never more than 2 orders of magnitude. Okay, so it's not the electrons versus the top, but I would take the tau versus the top. That's 2 orders of magnitude, and similar in the other generation. And here, all 3 generations are lighter by, so one of them is lighter than the tau, not by 6 orders of magnitude, but I think about 10 orders of magnitude. So I think there is something that requires a different mechanism, and the idea that these masses come from dimension 5, not like all others, so it's very different from just introducing right-hand neutrinos and giving Dirac masses with Yukawas that are 10 to the minus 12. No, this is a natural explanation of why the neutrinos are much lighter, and I think we need such explanation. So I'll finish with a light sentence, because so the fact that if the source of neutrino masses are dimension 5 terms in the star model effective field theory, I think it's very convincing that this is what we have discovered. We discovered the dimension 5 terms for me, okay? And the dimension 5 terms tell us that these are Majorana masses. And this is the main reason that I'm convinced in the sense that I'm ready to bet that they are Majorana particles. Another reason, I made this bet with someone, another reason that I'm willing to make this bet is that you cannot lose it. Why? Because you can prove that the neutrinos are not Dirac, but you cannot prove that they are not Majorana. We can discuss it later, but this is a bet that one cannot. But also I really believe that they are Majorana, and I believe because I think this is what we've seen in neutrino masses is dimension 5, and the main reason for that is that, first of all, I expect dimension 5, and second, it explains their lightness compared to any of the other fermions and massive vector bosons. So I'll stop here because we are late. Continue tomorrow.
So I have a question.
Yes.
So if we don't know the exact mass ordering for neutrinos, whether it is a normal mass ordering or the inverse mass ordering.
Yes,
So I am saying,
yes.
if we don't know what is the exact mass ordering for neutrinos, whether it is a normal mass ordering or inverse mass ordering, so how can we know that this 1 or 2 is nearby, is very near?
Oh, we know that there is, we measure two mass square differences, okay? We have these two numbers which are experimental. We measure these two. One that is a factor of what? 30 larger than the other. Okay, this is 30 times the other. And now, just by convention, we call the two that are involved in the smaller one Ne2 and Ne1. So it's not that. This is the identity of what Ne2 and Ne1 are. Okay, so it's by convention that we call the smaller one Ne2 and Ne1, and within this we call the heavier one Ne2.
Okay.
Convention. That's how we decide. Okay, your question would be analogous, just to make clear, to asking how do we know that the top is the heaviest and the up is the. But that's how we define what the top is and what the up is, because in all the quantum numbers they are the same. The only thing that distinguishes them is the mass. So the heaviest we call the top. That's our decision. Okay, it's a name. So similar here. It's a convention.
Okay.